Let's now consider some of the implications of this simplified barotropic Euler momentum equation. The Euler momentum equation for vorticity for a barotropic fluid. Recall this was for a system where the density took the simple form rho is rho of P, which also includes an incompressible fluid, rho being a constant. And if we have any body forces, the body forces were conservative forces given by a potential. We've assumed barotropic equation of state, but we have not assumed incompressibility to get to the simplified momentum equation form where the vorticity is given only by the curl of u cross omega, a nonlinear interaction. I want to consider two implications. First, for this system, if the vorticity is 0 at any time, well, the vorticity evolution, the change of vorticity in time is driven solely by the nonlinear actions of flow and vorticity. And if the vorticity is 0 at any time, then del cross u cross omega must also be 0. Which means that if the vorticity is 0 at any time, that the time derivative of the vorticity is 0, and therefore the vorticity, if it's 0 at any time, is 0 at all times. For all time. We call this special kind of flow an ideal flow with no vorticity anywhere in it, an irrotational flow. Irrotational flow, which is just a flow where there is no vorticity anywhere in space at that moment in time, and thus also under ideal conditions, no vorticity at any future time. Irrotational flows have a whole class of mathematical properties that make them amenable for straightforward solutions, so we'll see them a lot. They can be good approximations for understanding flow in physical systems too. The big thing that's different in real fluids is the presence of viscosity, which, as we'll learn, can generate vorticity. But irrotational flows are a very important class of flows. Let's make a second set of considerations for implications. So let's consider when vorticity is not 0. Let the vorticity not be 0, and let's consider the nonlinear term. What is this del cross u cross omega term? What can we learn from this term? Well, before we proceed, let's recall a vector identity. Del cross for any vector A cross any vector B. We can expand this into a collection of 4 terms. These are A times the divergence of B minus B times the divergence of A, and then we have plus B dotted into the gradient of A, and then minus A dotted into the gradient of B. So we have various combinations of vectors and derivatives here as we expand out our term. And they're all first derivative terms, which makes sense because we started with a first derivative term on the left-hand side here, and that turns into 4 different first derivative terms as we expand out the cross products. Okay. So our A and B are u and omega. So let us now rewrite our nonlinear term del cross u cross omega using this vector identity. So our first term, this is u times the divergence of omega. Okay, and then we also have omega times the divergence of u, and we have u dot grad, u contracted with the gradient, gotta get my things in the right order. So we have our omega dotted with the gradient contracting on u, because omega is our b vector and u is our a vector. Clean up our omega here. Omega, and then we have minus u dotted into our gradient of omega. Okay. Now, one of these terms is 0 for all cases. Recall the vorticity is defined as being the curl of u, and we have our very first term here, the divergence of the vorticity. That is the divergence of a curl of a thing. Here happens to be u. It doesn't matter what that thing is. By vector identities, that is 0 because the divergence of a curl is always 0. So the first term in this is 0, and we are left only with the 3 terms. All right, delightful. Let us write them down in our momentum equation. So we've got our d by dt of omega vector, and this is equal to minus omega dotted with the gradient of u, and we've got a plus the excuse me, I'm getting my signs confused here. Let's get these correct. This is equal to plus the gradient of omega dotted into u plus omega dotted into the gradient of u. We have a minus omega times the divergence of u, and we had a minus u dot grad omega. We're going to bring that over here, plus u dot grad omega. All right, so these 3 terms, those all come from our nonlinear term expanded out into its 3 different terms. Now, I've written it in this form because that first term we can actually recognize as a nonlinear advection term. This is an advection term. And we can combine this with our Eulerian derivative of omega to get a Lagrangian derivative of omega. So all of this is the Lagrangian derivative of omega, d omega dt. And the Lagrangian derivative of omega, this is omega dot grad, omega contracted with the gradients of u, minus omega times the divergence of u. This lets us pause and reflect the 2 different ways that vorticity can be changed in an ideal non-viscous fluid. So we can get it by this first term here or the second term. Let's start with the second term. This second term here, this is the compressible amplification of vorticity. Right, this is flow coming together, carrying vorticity with it as it goes, and putting more vorticity in the middle. So if we think of vorticity as these pink dots being carried in by a converging flow, then in the middle here there's a lot of pink dots and there's a lot of vorticity, and we basically squished the vorticity together and created more of it in a local region. So this is the compressible amplification of vorticity. What about this term here, this first term? This is omega dot grad u, and we call this the shear amplification of vorticity. This is vorticity that is that crosses the gradient of u, and this is stretching of vorticity by shear flow. So this is stretching of vorticity by shearing flow. And these 2 are the major 2 classes of amplification that can occur. Now let's consider one further simplification in our system. Not infrequently, we consider incompressible flows. So let's as a third and final simplification, let the flow be incompressible. Let div dot u equals 0. Then we have a very simple vorticity equation in the Lagrangian sense. We have d omega dt is equal to omega dot grad on the velocity u, with omega being the curl of u. In this system, the only thing that can change the vorticity of the flow are the nonlinear interactions of the flow, where the gradients of the flow, the shear gradients of the flow, stretch and amplify the vorticity. We'll see that this has a relationship to other vector quantities in flows as we proceed.